Okay, 2 o'clock on this beautiful Wednesday day. What's the temperature out there anyway? It's like high 30s at least, maybe like low 40s. Pretty nice. Saw some dude walking around with shorts and socks and sandals today. Very awesome. Pretty nice out there. Didn't even wear a coat today. It's nice. Homework number 3 is due right now. Oh, negative 1 minute ago. You're too late. I'll try to grade those early tomorrow morning. I'll probably post the solution tonight. Make sure you understand what's happening because we're going to build on moment concepts. If you don't know how to calculate moments, and we're going to build on that idea, you're going to be in trouble over the next week or so. Okay? Make sure you know what's going on there. Homework number 4 is going to be on some more complicated moment calculations and couple relationships, which we're going to talk about over the next few lectures. So that's going to be coming soon, probably due early next week, either Tuesday or Wednesday. So look for that coming soon. All right, these memes are too relatable, says Kanan. Yep, no doubt. All right, let's get back to where we were. So yesterday we were kind of breaking ground on some new ideas, and we introduced a new mathematical concept, which is the scalar triple product. And we talked about the scalar triple product with 3 vectors. Here, vector S, P, Q is S dot P cross Q, where we have the resultant of P cross Q being a vector, and then the vector S dotted with that particular resultant vector will result in a scalar. And the scalar triple product is going to end up being useful when we talk about the contribution of a moment about a specific axis, which I'll get to in just a second. But it also has sort of a physical meaning in that it is the volume of a parallelepiped. Gosh, that's actually hard to say. Say it like 3 times fast. It's going to be a tongue twister. All right. And here's a parallelepiped, and if you have 3 vectors sort of emanating from a particular point, then the volume of that parallelepiped is actually this triple product here. So you can maybe use that as a physical interpretation if you kind of like the idea of a physical sense of what's happening. So here's the particular volume of this object. Okay, so we sort of expanded this out and showed what this would actually look like. And remember, the result here is a scalar value. So we see a bunch of scalar pieces of information here that make up what is this triple product ultimately. And after expanding it, we sort of showed that it could be written in this, determinant form. And you saw the determinant form when we were calculating moments, where you had something like I, J, and K sort of on the top row of your sort of determinant chart here. But here now we have the scalar values of the S vector and X, Y, and Z that make up the top row instead of your I, J, K components. Now, when you kind of go through the math, you end up with what is the typical triple product result, which is kind of interesting. All right, so that was kind of a cool mathematical topic, but how does that now relate to moments? We were finally diving in on that new idea and trying to figure out what is the contribution of a particular moment about an axis that might not necessarily be aligned with the direction of that moment. And so we got into what is the moment of a force about an arbitrary axis. And we were looking at this using kind of this figure over here, where we have some force that exists out in space, this force A, and we have a position vector that locates point A from O, as you can kind of see from this image. We said that the moment that's generated from this force at A about the position vector, given this position vector, is this sort of moment here, MO. And this moment acts along an axis that is perpendicular to the plane that contains the force at A and the position vector RAO. And the question is, what is the contribution of this particular moment here about an axis that's not necessarily aligned with the direction of that moment, but let's say some other arbitrary axis here that we're defining with a unit vector lambda. And here we're leveraging our dot product or to project the contribution of this particular moment into that axis by saying that the contribution of this moment in this particular axis is given by the moment dotted into that particular axis with the m dot lambda here. Okay. So we were just about running with this idea and getting to the point where the triple product kind of comes into play and saying that, yes, the contribution is going to be something like lambda dotted with that particular moment. And now here we are with new material, but we know that given that the moment about O is just a position vector which locates A from O, crossed with the force at A, then the magnitude of the moment from the force at A about an axis coincident with lambda is, let's say, the magnitude of the moment along lambda, that might be a good way to describe it. This is a scalar value, is equal to that lambda dotted with the moment that we calculated as position vector arriving at A from O crossed with the force at A. Okay, and so here we are. This is the moment about an arbitrary axis, which here is like this lambda axis, resulting from the force at A that exists out in space that's at a position of RAO. And here this lambda is a unit vector along the direction of the axis of interest. Okay. So that's about where we were yesterday. And let me get this up here. And so that's the general idea. So let's now look at an example problem where we're actually working to calculate some of this information with some practicality. So let's look at this particular example problem here. So here we have this sort of cube structure, cubic with each side length being equal to A. And we have a force acting on one face of that cube between F and C. We want to determine the moment of P about A. We want to determine the contribution of that particular moment about the edge AB. We want to determine the contribution about the diagonal AG, and use some of that information to determine the perpendicular distance between FC and AG. So I'm going to bring this actually into the writing pad, and you can keep copying down if you need. Okay. So the first part of this is just like the homework that you kind of just turned in. We want to know what is the moment about A given this particular force. And there's no coordinate system particularly labeled on here, so let's go with kind of a traditional coordinate system here. And let's let this sort of out here be the x-axis. This up here will be the y-axis. And come out at me here. Let's let that be the z-axis, just so we're kind of on the same page with the coordinate system here. Okay. So first, I want the moment about A. Okay, well, that's pretty straightforward here. It's the position vector which locates F from A crossed with the force at F. All right. So my position vector that locates F from A, that's something that looks like this. Oh boy, that's not such a great line, but that's here. This is my position vector that locates F from A. So that's where I'm going to start here. Each one of these side lengths has a length of little a. So I think it's pretty easy to establish what my position vector, which locates F from A, is going to be. If I think about how far I have to go in X, that's just the value of A. Here we have little a in the I hat. And I have to go down little a in the J hat to get there. And I don't have to move anywhere in Z. So that's my full position vector. Here. All right. Now I'm going to want to write this force here is acting at F in terms of its rectangular components. I noted that it's sort of acting at the diagonal of this particular cube here. It's pretty easy to see that the angle that it makes with what would be like the XZ plane here, the angle theta, is 45 degrees. I'll just use that to sort of quickly define my vector here. So this is going to be crossed with the magnitude of P multiplied by the unit vector on which it acts, which here it's acting sort of up in the y direction. So here we're going to have sine 45 j hat. Okay, that would be like this contribution of the force. And adding to that, the contribution sort of in the z direction, which here is going to be acting sort of backwards, negative cosine 45 k hat. All right. So this is the cross product that I'm going to set up here. So let's go with the determinant method, just to make things crystal clear here. Okay, my position vector is A and I and negative A and J, 0 in the K. And if we sort of let sine 45 be root 2 on 2, and we're going to have 0 in the I. We have root 2 times the magnitude of P on 2 in J. And we have negative root 2 magnitude of P on 2 in the K. All right, so when this is said and done, we're going to execute our typical moment calculations. So kind of going down into the right. All right, well, I have some contribution there. I'm going down into the right, but generally what I get from this multiplication is going to be positive. And then I have a negative times a negative, so it's going to generally give me a positive. So here I'll have root 2 magnitude of P times A over 2 in the I hat. That's one term that we get here. Let's continue. Put it down and to the right. Okay, I run into some zeros there, so nothing from that term. And the K term here, down and to the right, I will have to consider. It's going to be a plus root 2 magnitude of P times A on 2 in K hat. Now we're going to finish our determinant by going down and to the left. So here we have I, 0, and root 2 P on 2. So since we run into a 0, that contribution is going to be 0. Down to the left here we have J, A, and negative root 2 P on 2. So I'm generally going down and to the left here, so I have a negative contribution from this portion of the moment. And I also have a negative entry on this particular diagonal. So generally I will have a positive contribution from this particular guy. So I'm going to end up with, along this route here, I'll end up with a plus root 2 magnitude of PA on 2. Right. In J. So all in all, my moment, I could just simplify this by sort of pulling this root 2 magnitude of PA on 2 out. And this is an I plus J plus K. Okay, kind of an interesting result, but we have a certain magnitude of our moment and it acts equally in I, J, and K. So if I thought about this in a little bit more practicality, if I was like standing at point A and I was interested in knowing, what is the contribution of this particular force here? Okay, well, I'll reach my arm in the direction of this force and curl my fingers in that direction. What I'm going to end up with is a moment that is sort of sticking generally in the positive x, y, z direction, sort of with equal contributions in all directions. And that's sort of what I see here. Equal contribution in both x, y, and z, positive direction. That's what I get out of this moment. So I'm generally kind of happy with that calculation. All right. So that's part A. Part B. Next thing we want to do is we want to know how much that moment contributes about the line AB. Right. So I've got this moment that I've generated. It looks like, this moment at A. And what I want to do is I want to project the contribution of that particular moment into the line AB. Right. So I want to know how much of that moment that I generate about point A from that force, how much of that moment acts along the axis that's coincident with AB. Right. So for this, I'm going to sort of enact my triple product idea, or my dot product if I want. So how much magnitude of my moment as A is along AB? That's the question. Okay. Well, if I wanted to define unit vector along AB, let's call that lambda AB. If I go back up to my figure and I think about what is the unit vector associated with that side of the cube, what's the unit vector that runs along AB? Speak louder. So I want to know what is the unit vector along AB. And AB is a side of a cube that's coincident with the x-axis, right? It runs parallel to the x-axis. So what unit vector is associated with the length AB? Unit vector. I hat, right? Okay. So in this situation, lambda AB is just I hat. Right? So if I thought about a unit vector that acted along this particular direction, that unit vector is I hat. It's just a vector of magnitude 1, which runs in the direction of AB. It's I hat. So if I want to project the contribution of this particular moment onto the line AB, I want to take the dot product between the moment that I generated and what is the I direction. So the magnitude of the moment along line AB is equal to this unit vector that runs along AB, which we know to be I hat, dotted with the moment that we generated at A. It's the dot product. So we know this to be I hat dotted with my moment at A. Which I'll write out fully here. We remember is root 2 magnitude of PA on 2 I plus J plus K. Now we got to kind of remember the rules of our dot products here to know how we execute this math. And we know that the dot product is distributive, so I can distribute this across the various pieces. And so what I got to consider is what is I dot I? That's the first thing I want to consider. What is I dot I? Who remembers from yesterday? Yeah, it's 1. Okay. What is I dot J? 0. Good. And I dot K? 0. Right? Okay. So the only real thing I'm going to be left over, or I'm going to be left with, is like this I dotted with I. That's going to, give me some contribution from that particular component. And the leading coefficient of this particular second term is the only thing that's really going to be left over. So the contribution of the moment AB, which here is like I dotted with something in the I direction from the moment. Here, the contribution along this particular axis is root 2PA on 2. So this is the magnitude of the contribution of the moment along this particular axis here. Okay. Notice that this is a scalar value. It's not a vector. There's no vector associated. I just want to know how much of the moment acts in the direction of I hat along that particular axis. All right. Now a little bit more complicated is part C. What is contribution along diagonal between, on this figure, which is point A and G? Well, again, the procedure is more or less exactly the same. We want to take the moment that we generated above point A, which is, what we calculated in part A of the problem, and dot it into a unit vector that runs along AG. So strategy here is that the moment along AG is this unit vector, which runs between A and G, dotted with that moment at A. So I need this guy. Okay, so let's go up to our figure and look at what lambda AG is. So lambda AG is a unit vector that runs along the axis between A and G. So that is this direction here, and we want a unit vector, which we call lambda AG. This is a vector of magnitude 1 that just points in this direction. All right, so how do we get a unit vector between 2 points if we happen to know 2 points in space where they lie? Kind of did this in our 3D problems. So this is going to be something like the distance that you have travel in x and I hat, plus the distance you have to travel in y and j hat, plus distance you have to travel in z and k hat, normalized by the square root of the sum of the squares, the distances between the points. Right? You guys kind of remember this from when we did this in 3D equilibrium. We want to define a unit vector along the direction of some particular axis or between 2 points. This is our method. So going back up to my figure, I want to think about going from point A to point G and how far I have to travel to get from A to G in these cardinal directions. Okay. Well, if I think about that, I've got to go kind of 1 unit of A in the x direction. I've got to go minus 1 unit of A in the y direction. And I've got to go minus 1 unit of A in the z direction. So I'm going to end up with something like AI hat minus AJ hat minus AK hat. Normalized by the sum of the squares of the distances. This is A squared plus A squared plus A squared. Or I guess if you want to be a little bit more exact, plus gonna end up with the same thing. Okay. So this is something like AI minus AJ minus AK normalized by square root of 3A squared. Yes? I could sort of simplify the denominator a little bit, pull the A out. So this will be A root 3 in the denominator. This A will cancel with the A's that are in the numerator. And you're ultimately left with a unit vector along this axis, which looks something like I minus J minus K, all normalized by root 3. Hopefully you learned in your math classes it's bad to have square roots in the denominator. So this is root 3 on 3 times I minus J minus K. And this here is a unit vector between points A and points G. So we're now ready for this dot product. My moment a day, I know from before, root 2, magnitude of P, A, on 2. We'll go back up here. I, J, K. Working through this, I'm really looking at just multiplying like terms here. So here I have root 3 on 3 I hat, root 2p a on 2 I hat. So my contribution that comes from the I hat component dotted with the I hat component is going to be something like root 3 on 3 times root 2 magnitude of p a on 2. That comes from my I hat component. Next, I have to consider the contribution from the j hat components. Okay. So I have a negative sign here, so we're going to have a subtraction. And lastly, my k contribution. Again, a minus sign because of the minus here. Okay. It's nice that some of these guys kind of cancel each other straight away. Like the I and the j contributions here will just cancel each other straight up. So it's nice. Finally, you're ending up with the moment about this particular line. Negative root 3 on 3 multiplied by root 2 magnitude of p times a over 2. Or if you simplify this, this is root 6 on 6 magnitude of p times a. You can put a negative here. The negative sign is just indicating kind of which direction it's acting. So it's kind of acting in the opposite direction that we drew our unit vector. So the magnitude would be root 6 on 6 p times a. Complicated. All right, so that is the amount that the moment contributes about this line here, this lambda ag. You know, so we sort of calculated what this moment was one more time here. and I want to dot it into this particular axis. I've done that, and I see what my contribution is. So it's more or less, how much am I more or less torquing about this axis, given a majority of my torque being sort of in this general direction from that force. Okay, lastly, D. This comes a bit from our shortcut methods that we talked about last time. So we know the magnitude of moment on an axis along AG is sort of root 6 on 6 magnitude of P times A. All right. We also know that the perpendicular distance between the line of action of a force and where a moment acts is the distance d. So remember our shortcut methods. That the magnitude of the moment is equal to the magnitude of the force times d. This is sort of from, I think, like the end of the week last week, where this d is the perpendicular distance from line of action of force to point of interest. Okay. So this d is going to be the shortest distance between our axis of interest, this AG, and the force that's acting is this force P. So what we're sort of looking for in this problem, just part D of this problem, is what is the shortest distance between the line of action of this force and this particular axis here. Okay. So the shortest distance between these two particular lines of action is the distance D, which is a perpendicular distance between the two of them. A little bit difficult to sort of envision here, but the perpendicular distance between them is the distance D. It's the shortest distance between the two of them. Last week, we knew that if we knew what the moment was about a particular axis or about a particular line, and we knew the line of action of a force, which is the line of action of this force P, then D is the shortest or the perpendicular distance between those two. So in this situation, the perpendicular distance between the two is the magnitude of the moment, which acts along AG, normalized by this force that we have, the magnitude of the force P, which are given. So in this situation, here D is the magnitude of this moment, root 6 on 6 magnitude of P times A, all divided by the magnitude of P, or that leads us to the shortest distance between these two particular axes is just root 6 times A over 6. A nice little trick. Complicated though. Okay, that's where we'll leave it today. We'll start in on a new concept tomorrow, which is the couple, force couple, new concept. See you then.